an introduction to redox reactions. We've been talking about, in Unit 4, driving forces. So, in reactions that happen often in aqueous solution, what is the reason for those reactants to undergo a chemical change? What inspires the breaking and making of chemical bonds? And we'll talk about the theory behind why, but just for now, if a reaction produces a precipitate, creates water, or a gas, we know that will be favored. But there's another. If we would take solid aluminum and react that with a solution of copper 2 nitrate, in time, we will see a change in that copper solid begins to form and collect on the aluminum. We know that copper plus 2 is that gorgeous, kind of this color in solution, and that actually, the color diminishes as the ion is being converted into elemental solid. If I could take a moment to balance this, we would need a 3 here, and a 3, and a 2. All right, so what is going on here? Because I'm not creating a precipitate. I'm not creating a solid from the mixture of 2 or more solutions. I'm certainly not making water. I'm not making a gas. Well, this falls under the category of redox reaction. All right. Well, here aluminum is neutral. It's in its element form. We know copper here is a positive 2 ion. Well, on the product side, aluminum is converting into a positive 3, and then copper is in its neutral form. So, what we have happening is aluminum is becoming more positive. The aluminum is oxidizing. Oxidation is the loss of electrons. How do we become a positive ion? We know this by losing electrons, and then we have more remaining protons than remaining electrons. All right, well, if this is losing electrons, is something picking up electrons? Well, here, the copper ion is converting to neutral. It's becoming less positive, and that is called reduction, or the copper ion is reducing. Reduction is the gain of electrons. I like the acronym of Leo the lion says grr. The loss of electrons is oxidation, the gain of electrons is reduction. We can also have oil rig, which oxidation is loss, reduction is gain. I gotta prefer that. That just makes more sense to my brain and is easier for me to categorize. It is the exchange of electrons, the transfer of electrons. So aluminum gives and copper takes. We don't know if it gives and then takes, or does copper pull and so aluminum gives. But we just know they happen simultaneously. They have to. You can't have something gain without something losing, and vice versa. You only will ever have a single element or ion losing and a single element or ion gaining. You'll never have 2 things oxidizing and 1 thing reducing, or 2 reducing, or 3 reducing and 1 oxidizing. So that's the way just our world presents itself. So this reaction is spontaneous, so we know the transfer of electrons, we could also say exchange, is one of our driving forces. So we come up with this nickname, redox, for the reduction and oxidation, but you can call it oxidation, reduction reactions, one and the same. So we use those terms kind of interchangeably. So how do we know if we're dealing with an oxidation reduction reaction? Well, we need to be able to assign oxidation numbers. All right, now first, what is an oxidation number? An oxidation number is an assigned charge. Okay, what do we mean? All right, if we have sodium chloride, we know that for this electrostatic attraction to hold this ionic bond together, we know that sodium has lost its electron. It is without, and the chlorine gained it, so it is keeping, and this is a full positive and a full negative. This is a full cation and a full anion. They're doing their thing. So this clearly is +1 and -1. But what about the case of water? Now we know that these are covalently bonded, and the electrons are spending more time because of the electronegativity of oxygen, and we assign this side more negative, this side more positive, and we probably even jump to say, oh, oxygen is -2 here and hydrogen is +1. But it's not a transfer of electrons like in sodium chloride. It's not a full, clear -2. It's just a partial charge. But we make the assignment of -2. In our humanness, we're trying to make an understanding of what's going on. So it's really an oxidation number. We're saying it's -2, even though we know it's really not fully. So an oxidation number, to kind of distinguish between charge, which would be what we would say sodium here and chloride is there, we usually write it with the number and then the sign following. So it'll be 2-. And then the hydrogens we are assigning to be 1+. But for our intents and purposes, we're okay writing it +1 or 1+. Now Zumdahl, from this point onward, will write oxidation numbers with the value and then the charge. So, how do we know what things are? Like in the case of phosphate, how do we know what the oxidation number of oxygen and phosphorus are? Well, there are some rules. And we just have to know how we're going to apply these, and these are right from your textbook. All right. Well, first, if you have an element in its element neutral form, it has an oxidation number of 0. So in the last example I was speaking of, I said we're going to take aluminum solid and react it with copper 2 nitrate. Well, this is the elemental form of aluminum. So it gets the assignment of no charge, oxidation number of 0. Now, our diatomic elements, even though it's a molecule and they're chemically bonded, that's the element form. So oxygen, hydrogen, chlorine, those would get assignments of 0 as well. All right, number 2. I could have said, okay, I'm going to react aluminum with the copper +2 ion. Now, if you are told the charge of the ion, that is the oxidation state. So I don't have to rewrite it, I can just acknowledge it. Or if I want to say, okay, I am making it 2+, it is this oxidation number. All right. 3 is an almost always, Oxygen, because of its great electronegativity, is almost always -2. So, in water, we're going to make it -2 or 2 negative. In phosphate, we're going to make it -2 or 2 negative. The only exception is when we are encountering oxygen and peroxide. For example, hydrogen peroxide. Here, O2 - 2 is a polyatomic ion, so each oxygen is 1-. So how will we know if we're dealing with peroxide? You will be given the name of it. I promise the word problem will read that you are reacting such and such with hydrogen peroxide. So there will be no doubt. So we don't have to be on guard whenever we have two oxygens in a formula. We have to be on guard when we're told the name is peroxide. Then we know it's 1 minus. Because of the electronegativity of fluorine, we know it has the greatest strength for pulling electrons toward it in a chemical bond. We'll talk about why that is to come. It is always then going to be -1. So that is an always. Oh, and I skipped one. Fluorine, the most electronegative. Poor hydrogen is so low in its electronegativity. We just go ahead and always make it +1. Okay, so we have some always here. Well, what if you have elements that aren't addressed here? Well, you're going to look at the difference in electronegativity values. The closer an element is to fluorine, the greater in electronegativity it is, and we would assign it the charge it will take on from its position on the table. And then, if you have elements in a compound, we know that the sum of their oxidation numbers must be 0. And we'll look at an example of that. So, to bring this to life, how about phosphate? Well, what I would always do is assign always first. So what do we know? We always know oxygen is going to be 2 minus. Phosphate has a -3 left over. This whole species carries that charge. If I have 4 oxygens and each is -2, collectively, that's going to give me a -8 charge, 4 -2s. So, my 1 phosphorus, what must its charge be? So when I add that to -8, I have -3 remaining for the polyatomic ion. So, +5. So the oxidation number would be 5+ for phosphorus. I should write that in blue, huh? Trying to keep consistent. All right. Let's look at a couple on the next page. Well, what about in carbon monoxide? Get a little closer. Well, what are our always? Oxygen, 2 minus. It's a neutral compound, so 1 carbon must be 2+. How about copper here? Be careful. That's the neutral elemental form. Neutral. How about here? You know that oxygen's 2 minus, iron 3+. What about here? We know fluorine is always -1, so 1 minus. Sulfur here must be 6+. What about in perchloric acid? What do we always know? We always know oxygen is -2 or 2 negative, hydrogen 1+. So my 4 oxygens gives me -8. Your 1 hydrogen is +1. So what must be the oxidation number of chlorine? So when I add these, I get 0. It's going to be 7+. All right. So I pray that little bit of explanation gave us some direction about redox reactions. The transfer of electrons is a driving force. How do we recognize it, and how do we assign oxidation numbers?